The next set of optimization problems that we have are what I call geometry. We're going to be looking at geometric shapes, and more distinctly we're looking at rectangles. Alright, so let's just review a little bit about rectangles. What we know for a rectangle is if we got a certain length and a certain width, right, the area is the length times the width. And then the perimeter is twice the width plus twice the length, right? So again, the area is how many square units do we have inside, length times width. The perimeter, we walk the width once, the length once, the width twice, the length twice. So the how much perimeter do we have is like how much fencing do we need, as opposed to in here, right, this would be like how much square footage of something that we need, like in terms of turf or whatever the case might be. If we were painting something, right, how much paint I would need, as opposed to how much trim I would need around the frame. Okay, so those are some pretty important formulas that we're going to use to maximize situations. So in the first problem, we got Raymond has 4,000 feet of fencing, and he's going to construct a rectangular garden. He wants to maximize the area of the rectangle. So what dimensions are needed? So again, we have a picture like so, and so let me draw a real quick picture, and we're trying to eventually maximize that, but we are limited by perimeter because they're told us that we only have 4,000 feet of fencing to put around. So that's just basically telling us that 2L plus 2W is equal to 4,000. So classic situation, again, notice that this has 3 variables in it and this only has 2. So here's your constraint, and here's what we're trying to try to maximize. As a matter of fact, we're told we want to maximize the area. So what we now need to do is find A. We can find it in terms of L, or we can find it in terms of W. It really doesn't matter which one, because we got to find the dimensions anyways. So let me go ahead and just solve this for L. So the first thing I'm going to do is divide both sides by 2. That gives us L plus W is 2,000. Subtracting W from both sides, we get that L is negative W plus 2,000. So if I now go substitute this up here, L we're going to replace with negative W plus 2,000, and W is itself. So what we finally have is a function in terms of W that gets the job done. And what we also notice, it is a quadratic model, right, because W is squared. So if we were to model this, right, we would basically get a parabola. So the maximum occurs again at the vertex. So it's all about finding that vertex. So what value gets us that? Well, the x-coordinate is negative b over 2a. In this case, it's negative 2,000 over 2 times negative 1. A negative divided by a negative is a positive. 2,000 divided by 2 is 1,000. So we know that this maximum area is going to occur at 1,000. And again, that's the width, right? That's W. So to find the length I need, we can just come over here. So the length is negative 1,000 plus 2,000. We find that the length is also 1,000. So for this situation, for 4,000 feet of fencing, for a rectangular situation, we actually don't need a rectangle, we need a square. All right, so we need a 1,000 by 1,000. Okay, that way Raymond has enough fencing, and we maximize the area of coverage that we need if that's what he wants to do. So there's your first geometry question. It all basically comes down to our 2 big formulas working together. And again, that idea, we use our constraint to solve for one of the variables, we substitute it in, and we now have a function that we can analyze using some of the things that we've learned in this class. Okay, so let me cut to a new video. We got a couple more geometry problems to do, but I'll do a video for each to concentrate on each one.